Welcome to Spring LIB.
So for this question, it says that a mass M sits at rest on a spring. So we'll draw the figure first. So we have the mass M sits at rest, and it is compressed by a distance d, it says. So that is the first part of the problem. And in the second part, it says, suppose instead the mass is released from rest. So which means that this is the unstretched spring, and the mass is released from rest at this location. And now when it is released, then it comes to some location here. So before it comes to rest, it falls a distance of d before it achieves equilibrium position. They're saying compare this d with this d. So we'll see here, first of all, in this case, when the mass is sitting at rest at this location, there are two forces acting here. We have the force of spring and we have mg. The force of spring is actually equals to kd is equals to mg. So therefore we get d is equals to mg by k. So we have the d here. Now in this scenario, we have the position 1 and position 2, and this is our point for zero reference level. So the mass is released at this location, and then it falls and comes to a point where it comes to rest at this location too. So we use conservation of energy. So we say E1 is equals to E2. The energy is conserved the locations. V1 is equals to V2 is 0 at both the locations because the object is at rest. Y1 is equals to 0 at this location here because this is a zero reference level. And Y2 is equals to negative D. Since this was our zero reference level, then y2, the distance which is falling in the second case, is negative d. So we'll apply the conservation of energy to that. So E1 is equals to half mv1 squared plus mgy1 plus half ky1 squared. Well, at location 1, there is no energy kinetic, there is no GPE, the spring is not compressed, so all the energies are 0. At location 2, the kinetic energy of the particle is 0. The potential energy we have just seen is equal to negative mgd. It's negative because it is 0. It is below the 0 reference level. And the elastic potential energy at that location is half k d squared. So if we solve this equation, we actually get d is equals to 2 mg by k. As you can see clearly by comparing this equation and by comparing this equation here, these two, we can see clearly that d equals to d. Now, what is the reason that two distances are not equal? Now, the reason that two distances are not equal is because, especially in this case, putting the mass at rest at this location, so somebody needs to be pushing it downwards and holding it in this position, to arrive at this position. The reason two distances are not equal is that when we put the mass at rest at a compressed position, it required some work in addition to the work done by gravity on the spring. And this work is actually not done by the conservative force, but done by some external agent on the spring. So that is your hand, basically, is doing external work in this scenario. So therefore, the two distances are not equal.